Hey everybody, hope you had a restful Thanksgiving break, and we're going to hit the ground running today with the concepts energy, work, and power. So let's get right into it. Make sure you've got your note-taking worksheet out and ready to go. And remember, you can pause the video at any time in order to fill in the blanks and complete some of the practice problems that we're going to go through today. So here we go. First, energy. New concept. Brand new concept. When we've moved on from projectile motion and all of that, and forces, though it's all tied together. This is a new unit known as energy. Now, energy. What is energy? Well, energy is the mediator of physical changes, meaning that it is what allows changes to occur. Okay, it's this concept, it's this thing. What allows movement to happen? What allows food in your stomach to be processed? Okay, what allows that to happen? Energy. Okay, so energy, such as changes in speed, height, temperature, chemical composition. It is not created or destroyed. That's a very important thing you might recall is the law of conservation of energy. We'll get to that as we go through this unit, but keep in mind that it's an amount, okay? And the overall amount of energy doesn't go up or down. It remains constant, but there can be changes to a type of energy. For example, the amount of mechanical energy could go up while radiant energy goes down. Because it can be transformed into another type. Okay, and energy allows work to be done, and we'll talk about what work is. Okay, so now all changes require energy, like I said, to flow or be transformed. And a big point is that energy both enables and limits how much change occurs. Okay. No energy means nothing can be done. Think about just you waking up in the day. You have no energy, you're not going to do anything. You have lots of energy, lots of things are going to happen for you. Okay, so that's basically what energy is. So energy comes in many forms. We're going to go through each of these forms you see listed here on the types of energy. The main key concept that you need to take away from this for, say, a semester exam that's coming up in just a couple weeks is examples of the types of mechanical, or not mechanical, but types of energy. Just examples of them is the key thing, okay? Being able to identify your types of energy. So, for example, mechanical energy. Mechanical energy, believe it or not, is what we've been talking about the whole year, okay? It includes motion and position. So everything we've been talking about, the ability to move one thing to one place to another, to speed up, to slow down, to change directions, all of that is mechanical energy. So think anything, projectile motion, whatever that we've already talked about, it's mechanical energy. So it includes kinetic and potential energy, which you should have learned about in middle school. And we're going to refresh on those concepts later this week. Now, as far as examples of kinetic and potential, just to really quickly give you an example, kinetic movement. Kinetic means movement. And potential means the ability to do something. So gravitational potential energy, raising something off the ground where gravity is going to give it energy. An elastic, think of elastics like the elastics on a face mask or whitey tighties or a rubber band or whatever. There is potential energy as you stretch a band to do work. Okay, you're giving it energy, potential energy. That's mechanical. And we're going to spend a lot of time on mechanical energy as we go through this unit. Now, the other types we're going to get into here in this list here are basically the concepts for the spring semester. We're going to spend a while on each of these types throughout the spring. So this is where you're getting this transition from the fall semester to the spring semester. We introduce this concept of energy and we run with it for the entire spring semester. It's all about energy, different types of energy, and the units related to those. Like we'll spend a whole unit on radiant or thermal energy. We'll spend a whole unit on electricity and sometime on nuclear potentially, sound, magnetism, all that stuff. That's all in the spring. Now, moving on with types of energy. So mechanical, movement, basic motion that we've been talking about. Radiant. Radiant energy includes the electromagnetic radiation. Radiant radiation. Visible light is actually a form of radiation. Infrared, ultraviolet, microwaves, radio waves, X-rays, the rays from the sun. That's ultraviolet. That's actually a lot of different types of rays. So radiant energy, radiation. Nuclear energy. Forces that hold the atom together. Nuclear, nucleus. Think of middle school where you learned about the atom. Okay, inside the middle of the atom is the nucleus. So nuclear energy comes from the nucleus of an atom. None of the rest of the atom. It's all about the nucleus. Changes the atom's nucleus, absorbs or releases energy. Nuclear bombs, nuclear power plants, the sun and stars are all examples of nuclear energy. Okay, that's what powers the sun, is nuclear energy. Electrical energy. So, electrical energy, electricity. It's electricity. Okay, moves through wires. It's the basis of all human technology. It's electrical energy. Okay, electrical energy comes from other forms of energy. So, in order to make electricity, we have to pull energy from something else. We have to take typically thermal energy, turn it into electrical energy. And we'll talk all about that when we get to thermal energy in the spring. Chemical energy, stored in the bonds between atoms, what we call chemical bonds. So you have nuclear energy, it's the nucleus, but then atoms are held together. When atoms are held together, there's a bond between them, okay? And when the bond breaks, energy is released. So chemical energy is that energy that gets released from those bonds. So when you eat food and it's digested, the energy is released from the chemical bonds inside of the food. That's where energy from food comes from. Okay, moving on. Thermal energy. Thermal, thermostat, heat. Thermal energy, energy due to temperature. It's heat. It's hot. No such thing as cold. We'll get to that later. This is actually the first of the energy topics that we get to in the spring is thermal energy, called thermodynamics. An object at a higher temperature has more energy than at a lower temperature. Bada bing, bada boom. Okay? And we'll get into all that later. Fluid pressure. Fluids, believe it or not, are not just liquids. Fluids include liquids and gases. So the pressure of a fluid is actually a form of energy. So if you think of the air inside of a balloon, there's an amount of energy from the air pushing the balloon out. It's what allows the balloon to be inflated, is fluid pressure. Okay, high pressure air in a bicycle tire has more energy than low pressure air. Pressure, more energy. Now, what is energy? Energy can cause changes. That's what energy is. Anything that causes a change. Now, energy is measured in a brand new unit known as joules. Joules. Joules, represented as a capital J, is the unit of energy. If it's a type of energy, it's going to be represented in joules. Okay? Bada bing, bada boom. Energy in an equation by itself is the letter E. It's a capital E in an equation. So capital E is measured in joules. Now, a very specific topic within energy is work. Okay, this is where we're getting into the equations. We aren't going to get through this unit without equations. We've got to have a few of them. 2 today, at least. Maybe 3. We'll see. But work. What is work? If I say do some work, what am I talking about? Well, work done on an object equals the force on the object multiplied by the distance the object moves in the direction of the force. So work is force times distance. Okay, work is force times distance. All right. Now, or displacement, really. Force times displacement, more specifically. So, work is a type of energy. So, it's measured in joules. Force, we've talked about force. It's in newtons. Distance is in meters. Distance or displacement. Now, what is work? Work is force over a distance. That's it. If you have an object and you make it move, did that take force to make that pin move? Ooh, look at that. Real life examples. This is a very expensive example. Might have cost me $0.25 to get this pin. So, if I take this pin and I push it, well, I applied a force, got it to move a distance. Work was done. If I can calculate the force, measure the distance, I can tell you how much energy was used. Boom, because every change requires energy, right? So the simple motion of this to here requires some amount of energy to do. Energy must go from my hand into the pin in order for work to occur, right? Now, work is done by forces that change the motion of an object. A force of 1 Newton over 1 meter is 1 joule. Okay, Newton meter. It's not newtons per meter. It's called a Newton meter. N times M. Newtons times meters. Newton meter. That's what a joule is. A Newton meter. I just like saying the word Newton meter because it sounds fun. So a joule is a Newton meter of work. Done. Next, 2 ways to do 10 joules of work. If I have, over here, 10 newtons of force over 1 meter, well, 10 times 1 is 10. Whew, big math. Instead, if I use 1 newton over 10 meters, 1 times 10, and again. It's just force times distance. It's simple. Don't make it too complicated. Force times distance. All right. Now, how much work is done if you push on a wall with 100 newtons of force? You push on a wall. Pushing on the wall. Does the wall move? Unless you're the Hulk. Well, probably not. Right? So if you push real hard on a wall, you could be pushing real hard. Pushing with all your force. If the wall doesn't move, work is not done on the wall. Work is not done on the wall. Okay? Because the wall didn't move. But instead, so in this definition, like I was trying to say, sorry, I didn't have the next slide previewed. I should have. But in physics, the definition of work requires the object move. So if the wall doesn't move, work is not done on the wall. But here's the question. Is work done on anything, right? If I'm pushing on a wall, pushing real hard, and the wall's not moving, but I am moving. Am I moving some distance? I am moving, trying to push. Every fiber in your arm, as you move, your muscles move in order to make a motion. So therefore, the contraction of your muscles is some distance. And a force is applied. Because if you're pushing on the wall, Newton's third law says what? It says that the wall is pushing on you. Right? If you push on the wall pushes on you. That's Newton's third law of motion. Okay? So as I push on the wall's pushing on me, and my arm's moving some distance. Wall did work on me. Okay, work is done by your muscles contracting. Okay? So the wall does work on your muscles. In fact, if you lift weights, right, you're pushing up the weights, right? But you're working out because as you push up, the weights are pushing down on your muscles. Okay? The weights are pushing down on your muscles. The weights are working on you because you're moving a distance too. Your muscles are moving a distance. Work is being done on your muscles by the weights. Work out. Okay? See? connections. Now, which force does work? So this is a 10-kilogram crate being pulled to the right with a rope across a rough surface. 4 forces are there. What are they? Okay, I'll label the forces real quick. So, let's see. We label the forces real quick, and we find that the normal force and the weight do 0 work because the crate does not move up or down. No work up or down, okay? Because it balances out. But if you look, you have friction and tension. Which way is work? Well, tension does positive work because work goes this way, right? Direction of the force, right? That's the direction it goes. Positive work being done. But at the same time, friction does negative work. Because, think about this. Force is still going that way. Friction is going that way. And a distance is being moved. So force is going that way, but the direction is this way. Opposites. So you have a negative force going this way, because remember, left is negative, and a positive direction going that way. So, negative force, positive direction, force times distance, negative times positive work. Negative force, positive distance, negative work. Tension, however, well, force is positive going this way. Distance is positive going this way. Positive times a positive is a positive. Positive force direction, positive distance direction, positive work direction, which means, going a little off book here, work and energy have an amount and a direction. Meaning, is it scalar or vector? It's a vector. It's a vector because it has amount and direction. All right. Power! Sorry. Anytime I see the word power, I feel like I have to be Arnold Schwarzenegger for a moment. This power, you feel the power. Do the power of working out. It's exciting. You lift the weights. Anyways, you're welcome. That might be an at-home special. I don't know if the people at school are going to get that, so feel lucky if you want to. Now, power, measured in watts. Any event in which energy is transformed involves power. Power is measured in watts, not J.J. Watt, the all-star player for the Houston Texans. Good old Watts, okay? W-A-T-T-S. Now, all power is measured in watts. Watts of a light bulb, watts in a car. Now, we also measure car power and horsepower. It's just another unit. Horsepower is just another unit for power. It's just used for cars, horses. Well, anyways. Okay, so what is power? Let's explain what is power and some examples of things with power. So anytime energy is being used or moved or transformed, power is present. So think about this. Is when we have an example like this. An elephant lifts a 300-kilogram log 3 meters up, 4 seconds. And it can lift several times its own body weight, 2 seconds. Which one's more powerful? So think about this. If you were wanting a truck to haul something, you need to have power. You need to do lots of work in a shorter period of time. There's lots of power, horsepower, okay? In this example, we really care about the amount of work. So in this case, the mass, force times acceleration, which is force over a distance of 3 meters. We would be looking at that as our work. So the elephant, of course, is more powerful. Okay, we always talk about ants as being pound for pound very powerful, but that's simply because they're little. Okay, but we're saying that the elephant can do a lot of work very quickly. Okay, so it's how fast is work getting done. Power is the rate at which work is done. Okay, power is the rate at which work is done. So power is the rate at which work is done. That is super important. If you're lifting weights slowly, there's a lot to be said for doing weights slowly. It's a whole nother kinesiology argument. But lifting a weight 1-2 times slowly is a different amount of power than lifting the same weight 1-2 times faster. Okay? The faster you lift that same amount of weight, you're doing the same work. Because think about this. If I lift a weight from here to here, there's a distance. It's a set distance from here to here, right? And a set amount of force required to push this from here to here. Now, the faster you do it, it's actually going to have a different acceleration. So, not the greatest example. But if I could apply the same amount of force, the faster you do it, the more power it is, because the rate you're doing work. Okay, so power is the rate at which work is done. Simply, it is work divided by time. So if you know how long work took, divide the work by the time, you get power. Is it? Okay. So a ball gains 1 joule of potential energy in 1 second. How much power does this require? 1 watt. Joule per second. So what is a watt? A watt is a joule, or Newton meter, per second. A watt is a joule per second. Joule per second. That's all. Okay? Joule per second. So 1 watt of power means that 1 joule of energy is transformed in 1 second. 1 watt of power also means that 1 joule of work is done in 1 second. Because they're connected. Energy, work, very, very similar concepts. Basically the same thing, to an extent. So, what is the power? Missed the question. A forklift raises a crate 5 seconds, giving the crate 500 joules of potential energy. What is the power of the forklift? So lifting it up, some sort of force, some sort of distance, giving it 5,000 joules of potential energy, lifting it way up. What's the power? Then it says, what is the power of the forklift if it does this job in half the time? Okay, so power, work divided by time. How much work? Well, we can identify the work based on the word joules. 5,000 joules divided by the time. 5 seconds. 5,000 divided by 5. 1,000 watts. Now half the time. Now think about this. We said if time goes down, we're reducing time half the time. If time goes down, what should happen to power? Should go up or down? Power should go up. Now, you do it in half the time, what's the change to the power? Half the time, double the power. Half the time, double the power. Okay? Half the time, double the power. 2,000. You can figure that out too. If you did 5,000 divided by 2.5, you would get 2,000 watts. Okay, notice watts is a capital W. Watts is a capital W. All right? Now, a runner might burn 1,000 calories. Believe it or not, calories is another unit of energy. Horsepower for power. Calories is another unit for energy. There's different units that mean the same thing, okay? in an hour. How much power does this correspond to? So a runner might burn 1,000 calories or 4,180,000 joules in an hour. How much power does that correspond to? Okay. Now, you have to do a little bit of unit conversion. That a unit of 1 hour is equal to 3,600 seconds. So really what we're doing here is the amount of joules divided by 3,600 seconds. Because remember, it's got to be joules per second to get watts. Joules per second, Newton meter seconds. Okay, now if you set that up, 4,180,000 divided by 3,600, you end up with 1,160 watts power. So if you can burn 1,000 calories in an hour, bada bing, bada boom, you're producing 1,100 watts of power. Good for you. Now, practice question. I like practice questions. Nala does twice as much work as Mateo in the same amount of time. How much power does she have compared to Mateo? So if Nala does it twice as much work than Mateo, how much power does she have? More or less. Twice as much work? Well, twice as much power. Okay? Alonso and Arena do the same amount of work, but Arena takes twice as long. Okay? Arena takes longer. More or less power? Longer, less power. It's being slow, less power. Slow, like a slow car. But how much? If it's twice as long, is it a quarter of the power, half the power, a third of the power? Well, if it's twice as long, then Arena has half the power, meaning Alonso has twice as much compared to Arena. Okay? So if you were to double the work, you double the power. If you triple the work, you triple the power. Things like that. So if the average unit of power in a sports car is 84,100 watts, it's a big number. There's another way to express this. We can convert it to kilowatts, okay? So if we know the amount of wattage in a sports car, we can convert that to kilowatts, okay? Kilo means 1,000, just like doing King Hair, Die by Drinking Chocolate Milk or the metric system. We can convert this to kilowatts, and so if you divide it by 1,000 or move the decimal over 3 places, we find that it's 84.1 kilowatts. Okay, so that's another way to express the amount of watts is something called kilowatts. Okay, we can also express it in a unit very common to cars, which is horsepower. Horsepower is 746 watts. 1 horsepower. Okay, so it's another random unit. 1 horsepower over 746 watts. So we can find the amount of horsepower in a car. And just know that this is the average power output for the event. Each instant is increasing as the velocity increases. But we could figure that out by taking that total amount of watts and dividing it by 746. So if we take that value, 84,100 divided by 746, you get 113 horsepower. So this is just an idea of example. How do you figure out horsepower? Okay, if you know it's 746 watts, 1 horsepower, total watts, divided by 746, you can figure out the horsepower in an object. Okay, usually used for cars. If we twist our power equation, which is change in energy over change in time, or work divided by change in time, and twist it around, we can figure out how much energy is being used. Notice they're just moving things around in an equation to get energy equals power times change in time. Okay? Now, why is this important? You ever looked at an energy bill? if you ever looked at an energy bill, you'll notice there's a funny unit for determining how much money you pay for your electric bill called kilowatt hours. Kilowatt hours, power, watts, time, hours, okay? And so you can actually calculate, using the equations we know, we can figure out how much energy is used by your appliances. Believe it or not, your toasters and things will say they use like 800 or 1100 watts of power. So if it says, for example, a toaster oven operating 800 watts takes 1.5 minutes to toast a bagel, how much energy is this? So if you take the watts times the time, that's 90 seconds. 800 times 90 is 72,000 joules. Again, you get this huge number. But we can change that to the unit I just mentioned, which is kilowatt hours, how we can convert these things, okay? Can express doing joules, kilowatt hours, okay? That's very simple. Kilowatt hours, you convert your watts to kilowatts, like I just showed you a little while ago, where you move the decimal over 3 places. And you have your time in hours. So make sure your time's in hours. Kilowatts times hours, and there's your unit. There's nothing shorthand for it. It's very simple. It's a kWh. kWh is kilowatt hours. Written out, it's got a little hyphen in between it. So we can actually express the amount of energy being used 2 different ways, joules or kilowatt hours. There you go. Okay. Now for you, I would like you to work through some of these practice problems at the end and figure out just kind of an assessment on your own of what is in each of these pieces of the equation and some example problems. Okay. Now, we're going to practice all this and more in the next bit, where we do a worksheet tomorrow, and we'll have even more with kinetic and potential energy later in the week. Okay. So, but for now, I've been Mr. Peritano, and this has been Energy, Work, and Power.